to do topology, which is very physicsy. I
I
think that
see.
is basically the core of physics.
I see. That's good. Yeah, and the vertex operator algebra is related to the monster group as well. So
Right, it's all connected.
yeah, I think from what I understand, the vertex operator algebra is um they want the goal is to define it for all quantum field theories, but then I think it's only rigorously defined for 2D CFT, right? From what I saw on Wikipedia.
Yeah, apparently, I don't know if it's generalizable to higher dimensions. That would be cool. Um, I don't know what's going on, but yeah, I'm interested because 2D CFTs are so like a lot of are very good to study mathematically rigorously, and they're also related to all the stuff like mirror symmetry and all that. So it's very relevant, very cool,
Mm,
very good.
yeah.
Um, yeah, and like I have a strong belief that all of physics can be understood mathematically rigorously because the parts of physics that cannot be understood mathematically rigorously, uh, like my basic thought is that physicists are doing something, and the manipulations are that they are doing at some formal level are always rigorous.
Mm,
It's just that like they interpret what those results mean in a more
and wavy way.
le yeah, in a more lenient and hand wavy
Mm,
way. But whatever they are doing in itself is always rigorous,
mm,
because it's just calculations and math.
mm,
So the key is to formalize that part and use it to make a bridge between analysis and algebra. And I think
mm,
that will give us at least like a 90% understanding of physics mathematically rigorously, and the
mm,
other 10% will be really hand wavy stuff. Um,
mm.
but yeah, so I think that's reasonable.
Cool,
So
cool.
the code CFTs are new, and I think like people Witten wrote one paper related to it. But like Witten hasn't really like totally gotten big on this topic.
Mm,
So it's new and Witten hasn't done it yet. So it's kind of like not really well structured yet.
mm.
Um
When
yeah,
Witten
like
comes in, it will be well structured.
yeah, everything gets structured when Witten starts to get really interested in it.
Mm,
Um but I think the idea should be understood as so. There is a connection between codes and lattices. And there's a connection between lattices and conformal field theories. Um, this part is interesting if you're interested in like theoretical computer science. This part is more interesting if you're interested in high energy physics. Um,
mm,
and when people write papers, they utilize this knowledge and this knowledge, and they basically write this connection as the title of their paper. But to be honest, this is kind of clickbait. Because like it's for me, it has been kind of more how should I say this? More insightful to study this connection and this connection like respectively, and then use those results to arrive at like the title of the paper. But like the I think it's more important to study the connection between lattices and CFTs instead of codes and CFTs. Lattices aren't like just an intermediate step, rather like each of those connections are more important than the entire connection. Um so yeah, that's my take. Um and like in the construction from lattices to codes to lattices is actually quite trivial. Because is basically a code word is basically a set of numbers. So A, B, C, D, blah, blah. It's like a string, um, which immediately has which like has a connection to a vector, um, in some space, and if you have a bunch of these vectors, then the span, the integer span becomes a lattice. So this is actually the basic idea of the correspondence, which is very intuitive and very simple. Oops, I accidentally left the whiteboard. I'll be coming back. Yeah, so it's quite intuitive. It's very simple. You just have the lattice, you just have the codes as some code words. The code words are equal to multidimensional vectors, and you just consider the lattice with those vectors as spaces. It's very intuitive in that sense. The connection between lattices and CFTs is also kind of intuitive, I guess. You can approach this in many ways. One way to think about this is like you imagine like, well, CFTs can also be understood as like some types of sigma models, or like a type of a bosonic string, or a fermion or a superstring or whatever. And like you basically consider us, and like one thing, so you need, if you know two things, it helps. One thing you know is strings on some space, and the other thing is if you have the knowledge of a point particle on some space, or a particle on a torus. So if you have a particle on a torus, this tells you that the momentum forms a lattice. The momenta form a lattice because of the periodic boundary conditions. This is a quantum mechanical effect. I think that's pretty reasonable. If you consider the Fourier transform of this, it's basically equivalent to saying that if you have a particle on a lattice, then the momenta live on the torus, which is basically the Brillouin zone. So this is the Fourier transform of that statement. And if you have a string, the situation is not very different, because a string is, you can think of the momentum of the string, and the momentum of the string forms a lattice. So there's this very reasonable way of thought of basically taking a string and putting the momentum of the string on a lattice. And that is basically the connection. If you have a lattice lambda, then you can basically consider a CFT with the momenta living in that lattice.
I see. So is it right to say okay, in string theory the worldsheet has a 2D CFT.
Yeah.
And if we constrain the momentum of this string to be in the lattice, then that would result in, roughly speaking, the string, it will correspond to the string being a sigma model living in some space.
Yeah, but like our actual construction will be more abstract, and we will just construct a vertex operator algebra directly from the lattice.
I see. Is it right to say that the strings, like the space they're considered, must be compact because like the torus is compact?
I think the best thing you can say is that for simple models, you would have a compact space. But for like, I think like because we're usually going to construct an abstract vertex operator algebra, you wouldn't immediately see the sigma model structure of it.
I see.
So we're not going to define the conformal field theories by using an action.
I see.
We're going to define a VOA. But the interesting thing is that there's multiple ways to define a CFT, which I'm going to write in this box here. So like if you're like just doing usual physics, the normal way to define a CFT is with an action. You have an action and then you see if it doesn't have any anomalies. Scale anomaly. If it doesn't have a scale anomaly and is classically scale invariant, it's usually conformally invariant. An example of a field theory that has a scale anomaly is a pure Yang-Mills. But anyway, like an action without a scale anomaly.
Wait, sorry, could you so the last statement was important to me because you said that an action that has scale invariance and has no anomaly is usually conformally invariant as well.
Yeah.
I see.
I mean, if yeah. So like I'm just gonna write this on the left because like there's the usual stuff, like there's like scale invariance.
Is there a reference for this? Because that's something that is quite an important statement because in like IC models.
I think it's no, it's not. It doesn't really have a proof. So I'm just gonna list three things here. I'm gonna list scale invariance, conformal invariance, and Weyl invariance. So they basically fall into being like this. So if a theory is Weyl invariant, it's conformal invariant. If a theory is conformal invariant, it's scale invariant. But it might be scale invariant and not conformal invariant. So in quantum field theory, we usually assume usually like all of these are usually always conformal invariant. Like I don't know how this is. There are arguments for it, and like this has been proved in specific dimensions and whatever. But yeah, it's just like physicist knowledge. I don't know. You will see statements similar to this in any like introductory conformal field theory course, as long as it's good enough.
Sorry, the Weyl invariance, I thought that was synonymous with conformal invariant. What's the difference between?
Weyl invariance. Oh, this is in the case where like the Weyl anomaly. So Weyl invariance is when the trace of the stress tensor is zero even on a curve manifold. For conformal invariance, you just need it to be zero on a flat manifold.
Ah, I see. Cool.
So yeah, you can define a CFT from an action. And that usually, I think this is reasonable enough to like guarantee modular invariance. Because like in that case, it's clear that the partition functions at higher genus are given by some path integral over an action functional, and that will have to be modular invariant.
When you say
But
modular
another
invariance of the action, you mean modular invariance of the partition function, right?
Yeah, the
Okay, sure.
partition function. Because I mean, if a partition function has a path integral form, then clearly it should be modular invariance by definition. But like another way to define a conformal field theory is by using a vertex operator algebra. In this case, modular invariance is not guaranteed.
I see. Actually, on that note, could you elaborate a bit more on modular invariance of the CFT action?
It's not modular invariance of the action; it's modular invariance of the partition function. But basically, it's like you have some Riemann surface, and you calculate the partition function on it.
So the partition function is the trace of the or is it the path integral? The path
Yeah,
integral
it's roughly the path integral, I guess. That's yeah. I mean, like you define it in some way. Like it has to be modular invariant because the modular group is basically a subset of the automorphism group of the underlying manifold M, and the path integral has to be invariant under automorphisms.
I see. Okay.
So like one example of the modular group would be on a torus. So consider that a torus is just equal to so imagine that you have a torus, right? The torus is just equal to a coset of R2. So imagine that if you have a torus, which is kind of given by this square. So basically, this point, this vector, and this vector are identified to zero, which is a torus. We can consider the map that basically, see, we can consider the map that basically shifts at each point from x, y to x plus y and y. So it would shift this square to this square. It's still the same torus. But we can see that this transformation is not continuously connected to the identity. So it's in the mapping class group, and it's also in the modular group. And and clearly, because this is an automorphism, the path integral should still be invariant under this transformation.
Mm,
Because it's just a relabeling of coordinates in some sense.
see. With regard to I see that they say that the model invariance is the group of large automorphisms, large diffeomorphisms of the torus, right?
Right.
What's the definition when you talk about a higher genus?
It's analogous. It's basically the group of large diffeomorphisms, modulo some other things that are in what I think what's called the Torali group or something. Um,
Um,
I think so. Wait, I think there was. If you go into the mapping class group Wikipedia article, there was a good exposition on it. I think if you could try
in class
searching
group.
for that.
I see. Okay.
Yeah, and just like keep going down. There is something I think. You have to go like a lot down, I think. Okay, yeah. The Torali group part.
Oh,
Right. So, yeah. So the symplectic group on basically the right of the chain, right.
I
So
see.
basically, yeah. The
Cool,
symplectic
cool.
group is the modular group at higher dimensions.
So for genus 1, SP2Z, SP2Z is in fact is in fact SL2Z.
Right.
And for higher genuses, it'll be this. I
Right.
see, that's interesting. How much of this Tor functor do you have to know? Will you say that it's good to know?
I mean, like, I think physicists only care about the modular group and not the entire mapping class group. Because I think like the partition functions are trivially invariant under the Torelli group.
Mm,
So it's only kind of non-trivial to check the modular group. I think that's the reason why. I'm
I
not
see.
sure. I haven't studied it in detail.
Cool. That's interesting. From what I read, something along the lines of when you want to construct the higher genus surfaces, like we know that for torus is parameterized by a parameter tau, right, of
Yeah.
where this guy is. It's like 1 and tau, right? Something along. Wait,
Yeah.
that will be
One in tau.
1 and tau. Um, but then for higher genus surfaces, like something like you can't really construct it out of a 2 R2. You must yeah, the construction is a bit more involved. So I
Yeah,
suppose
it involves a matrix, and the symplectic group acts on that matrix or whatever, I think.
I see.
Um,
Oh,
yeah, it's
okay.
a thing.
Okay
Um,
then. Cool.
so yeah. Um,
All right, yeah, let's get back
s-
to the topic. You're talking about
but
but
it's a very important topic, and
mm,
so I guess like the key here is that basically if you can define a conformal field theory, if you can define it on like arbitrary Riemann surfaces of arbitrary genus, you have a well-defined conformal field theory.
mm,
But it has to be modular invariant at all genus, and you have to check that. Um, in the case of the lattice to CFT construction, people construct the vertex operator algebras on the plane, and then they check modular invariance at genus one by calculating the partition function,
mm,
the torus partition function, which can be done with the which can be done because if you see here, I draw a picture, the in radial quantization, right, if you have like the plane, then you can understand it as being the Euclidean path integral is basically for like this, and this is
mm,
basically equivalent to like the cylinder.
mm,
And like if you take this and then if you take a cylinder of finite length and you glue the ends together, you get the torus partition function. So you can
mm.
check the modular invariance in that way by calculating the torus partition function and seeing if it is indeed modular invariant.
I see.
So that's what these people usually do. But on the topic of higher genus modular invariance, I don't think it's very clear for some of the models that have been discussed in the literature. Most of
Mm,
the most famous models are modular invariant, And one of the models called a Narain CFT is defined using an action functional, so it definitely has to be modular invariant. Yeah, but like for some of the other models that were discussed in the literature, I don't think their modular invariance has been checked.
Could you
Right.
drop some archive links about this for the
Sure, let
torus
me
case?
about the tourist thing, I don't know. It's like it's a very standard thing.
I see.
I don't know. It's basically everywhere. Let me just like refer you. Let me just refer you.
This looks like a fun topic because it involves Riemann surfaces and stuff like that.
Well, maybe, or maybe not. I haven't looked into it in detail. But like all of the research being done currently on code conformal field theories aren't really that clever, mathematically speaking. They're basically just doing some classification of 2D CFTs, and it's not really, there have been some connections to the monster CFT, which is quite nice. But it's still a little bit sophomoric currently. Right, let me see.
Wow, Monster CFT looks interesting.
Yeah, it does. But I haven't studied it yet. I'm not sure. Yeah, CFDs are interesting. Let's see here. Maybe let's see. Maybe you can take a look at 2009.01244. It contains a lot of stuff about what is usually done in this field.
Oh, sure. Yeah, I've been trying to read a bit of that in my
Yeah, it is a bit underwhelming. But like a lot of theoretical physics papers are underwhelming. So, I'm not saying that it's bad. I'm just saying that it's not really as cool as the title suggests, but it is still pretty cool. Right. So yeah, that's it. And anything else I say about this would just be in the details.
There's a interesting thing I want to elaborate a bit about the codes and lattices aspect.
Yeah, I can write that in one sentence. So I guess like there's a classical version and a quantum version. The quantum version is for stabilizer codes. The classical version is for classical codes, but they're all very simple. I could like say it in a nutshell. So I'm going to give two examples, two very boring examples. Okay, so let's see. And I'll be able to explain all of this in under 5 minutes, both the classical and the quantum case. So I'm going to draw a box down here. It's going to be very simple. So I'm going to consider a classical code, which basically maps 0 to 0, 1, and 1 to 1, 0. Or maybe the other way around. Have 0 to 1, 0. 0, 1 to 0, 1, or whatever. It's not very important. Okay, then you can map this to a vector. Oh, I accidentally left again. Let's see, let's get back in. Okay, just wait a sec. All right, so let's see here. Okay. You can map this to a vector in Z2n, where n equals 2. It's equal to 1, comma 0. This is equal to 0, comma 1. And then you basically map this to a vector in R2n. Is equal to, you divide by square root of 2. Okay. And then you basically consider the set of basically 1 over square root 2 c plus 2v. V is in z to the power of n equals 2 in this case. So it's basically these, plus all things of the form of 2n comma m, where n and m are like integers. This forms a lattice. Let's see
Sorry,
what that
what
lattice.
is C?
Oh, C is a code word.
And is that a reason why you use 2v instead of v?
Yeah, C in this case would be 1 comma 0 and 0 comma 1.
I see.
So it's very simple. You can draw this out. You have to. So if you have like you have the 2 points here. This 1 over square there's this dude and there's this dude. And then you have the sum of that. Because the sum of 2 code words is also a code word. Right. Oh yeah, I had to mention that. Right, we are going to consider additive codes, where basically the sum of 2 code words is a code word. Oh,
Sure.
we
Linear codes basically.
right, linear code. So 2 maps to 1 1, I guess. Oh yeah, and like, this is stupid. Let's see here. Let's erase this a bit. Okay, to make this an additive code, I'm just gonna 0 maps to 0 0, 1 maps to 1 0, 2 maps to 0 1, and 3 maps to 1 1, I guess. That's the code. And so you have all these points. And then you have the points that are shifting them by square root of 2. So you have these points up here, these points up here. So it forms a lattice. And in this case, the lattice is just the lattice with the lattice is just square root of 2 in this case. Cool. And there are some interesting properties that are easy to prove. So if the code is self-orthogonal, and there's a lattice, the lattice is integral. And if the codes, and you have a dual code, then you have the dual lattice. And you have a self-dual code, you have a self-dual lattice, and so on. Yeah, the definitions coincide under this map, which is fun. And for the quantum case, it's basically the same thing, but with slight differences. So when you have let's see how to say this. The quantum case is quite similar. If you have a stabilizer code, the stabilizer code could be, I don't know, ix, y, yi, yx. This might be the stabilizer. This one may be the stabilizer group. So we map x to 1, 0, z to 0, 1, y to 1, 1. So these map basically to 0, 0, 0, 0. These map to 0, 1, 0, 0. This maps to 1, 0, 1, 0, and this maps to 1, 1, 1, 0. Yeah. And you can see that. And basically, you follow the same procedure for these guys that you did over here in this case, in the classical case, and then you get a lattice in R4. But in this case, you define the metric differently on R4. Instead of using the metric that looks like 1, 1, 1, 1, what you would do is you don't use this metric and you use this metric instead. So you use the Lorentzian metric. So instead of calling it R4, call it R2, 2. The reason we use the Lorentzian metric is as follows. This is basically because it's more natural. Because in this case, you can see that the fact that stabilizer codes commute, stabilize or commute with each other, basically corresponds to the fact that lattice is integral. If you use this Lorentzian inner product, and that's why it's useful. It's all just constructions. This is the short version of it is really quite simple. It's really quite simple, and this is explained in detail in the paper that I just listed above. It's really not much.
I see. There's something interesting on the with regard to the I would say the classical case. It's actually it actually corresponds to, roughly speaking, sphere packing on lattices. Because I see the paper, they do mention things like linear programming and some bounds, right? Some G, I forgot the name. They mentioned some. They have graphs like let me find it. They have graphs like this: Gilbert, Marshall-Morph bound, and linear programming bound, and so on. And like I from what I understand now, the sphere packing problem can be solved by a bunch of linear programming. At least that's the current methods that work. The sphere packing, it corresponds to how many high dimensional spheres can pack into some space.
Yeah.
And this is related to linear programming. And one way to interpret this lattice thing is, if we map let's say 0 to 0 0 and
Right.
1 to 1 1, right? Then this is a 2D case with two bits. Then if we consider the lattice as follows, and the edges represent bit flips, right?
Right.
Flips of just one bit alone. So this is a 2D case. In the 3D case, it'll be a cube. In the 4D case, it'll be a hypercube, and so on.
Yeah.
And if we map 0, right? So these are the code. These are the codes, and these are the representatives. Or I don't know what's the I'll just call them the representatives. Or is it the other way?
Oh yeah, they're the code words. There's a code.
Yeah,
They are the code.
These are the code words.
Yeah, they're the messengers. No, the ones on the left are the messages. The ones on the right are the code words.
Right. And these are the code words. So if we consider it's a selection of code words on the lattice, such that they are maximally distant apart. So if I have some lattice this is just a general lattice, but a general graph in graph theory, if you, let's say, select this, right, then here's distance 1 away, then this is distance 2 away, and if we continue, maybe this distance 3, distance 4, and so on.
Right.
So something like that. Yeah. So these are distances on a lattice, which is studied in graph theory, and yeah. So we are looking for things that are maximally distant. So like distance apart. So essentially each of these have a certain radius on the lattice. So like radius 1 would be this guy, radius 1 would be these guys, radius 2 would be these guys, and radius 3 would be these guys, radius 4. It kind of defines a so-called sphere in a lattice.
Right.
And because we want the cowords to be far apart, that corresponds to packing as many spheres as possible into the lattice. And that's where it involves a bit of computer science and math.
Yeah. I guess so. I haven't looked into it, but the sphere packing problem and the maximal distance is also related to the spectral gap in the conformal filtering, and I haven't studied that yet. I have to be somewhere. I'll be back in about 2 minutes.
Sure.
Right. So yeah, that's it. This is actually pretty simple. It's kind of it's kind of interesting because like intuitively you can't really it's hard to see how one would go about constructing a conformal field theory from a code because these two things appear to be very distinct.
Mm,
If you were to tell me that we could construct a conformal field theory from a Kähler manifold, that would make sense because like you would go consider a sigma model on the Kähler manifold. But about in the code case, basically the connection is that you have a connection between codes and lattices, and then you can construct a conformal field theory from a lattice um, by considering a conformal field theory where the vertex algebra is basically constructed based on the lattice. Um,
mm,
so it's a little abstract if you want to see it in an abstract way, and it's useful because like we can wonder if like if all CFTs are lattice CFTs in some sense. Like these
mm.
types of questions are interesting and worth studying, I guess. Yeah, mathematically, I don't think mathematicians would be very interested in this just yet because it hasn't really provided a really new and interesting framework mathematically yet, I think.
It could be that this might shine some light on sphere packing in future.
Maybe. But I mean, it might be a stretch, you know?
Mm. Yeah, I mean, hopefully the hope is that Witten will come along and do what he did for the Jones polynomial.
Yeah. Uh,
Yeah, it would be
yeah,
great
so,
if he can like prove some bound or construct some example of a sphere packing in other than 8 and 24, right?
well, I think something similar has already been done, but I'm not sure how it would relate to CFTs. And I don't know, uh, I'm wondering if it would just be contrived, so, like clickbait paper, or if it would actually be important. Um,
Mm,
but I don't know. I think this studying this just motivated me to study CFTs more, from the
yeah,
vertex operator algebra perspective,
yeah,
which I think will
definitely.
be helpful in the future. But right now, I don't really have any big views for the field yet,
Mm,
because I'm still like studying the basics.
cool,
I
cool.
just have a better idea on what to study.
You actually
And I
got me
don't
a
think
little interested here.
yeah, it's just like some vertex upward algebra thing. Like I don't know. Like currently, my biggest goal is to study theoretical physics, like the mathematical tools of quantum field theory from a completely mathematically rigorous perspective, which I
Mm,
think is possible. And by doing that, I would be able to like bridge the gap between pure math and theoretical physics a bit more. Um,
mm,
because like right now, currently in the 21st century, like I feel like a lot of physicists in the last century, they came up with these like really interesting ideas that motivate a lot of mathematical structures. And those things were basically all coming from gauge theory and string theory and quantum field
mm,
theory. But now these days, like everyone just got lazy, or maybe everyone just doesn't like string theory, and everyone just doesn't want to do the type of things that are pregnant with mathematical meaning, and are just doing
mm,
something similar, just doing something very physics-y, but not of interest to mathematicians. So I
mm.
think that's sad, and maybe I'm wrong about this, but like maybe I should like study the things that were left behind in the last century and trying to like um bring the mathematical physics, physical mathematics, interdisciplinary thing to fruition more.
Mm. Do you want to bet when Witten will write a paper on this?
I don't think he will.
You think he will? I see. Is he what is he up to recently?
He's doing some stuff on. He's doing more physics-oriented stuff.
I
He's
see.
studying quantum gravity from the perspective of von Neumann algebras. But
Mm,
I don't think he's super serious about it. Maybe he is, I don't know. But his work is not really interesting to mathematicians, I think, compared to his other works. That being said, I'm not saying that his work is bad. His work is absolutely epic. It's just that his other works are even more absolutely epic because they deal
mm,
with things like Langlands. Nowadays not so much. But yeah.
Cool. All right. Yeah, that's interesting. Thanks for sharing this. In fact, I've been trying to read this paper, but I've been trying to read it, but I've gotten a bit stuck at a few of the earlier chapters, and that led me to watch some videos.
Mm,
This guy has this Dimaski guy, he has some lectures at IAS.
that's nice. Yeah, it's a pretty readable paper, but I would say it's readable, but it's not as well written as a paper by Witten.
Mm,
That rhymed for no reason, but yeah, Witten writes papers really well, and I think like some physicists, when they do research, they don't like study everything they need for the research in
mm,
a very comprehensive way, so they just write the paper based on what they know, and this
mm,
leads to very inefficient like
mm,
exposition. Like
mm,
I'm the type of guy that likes to study, do the prior study, do a lot of prior studying, so I can get the most efficient and clear cut logic possible.
mm,
Maybe that is a bit of a maybe my thoughts will change in the near future, but like yeah, I do like to spend time
mm.
studying the basics.
Cool, cool. Yeah, all right. Thanks for the sharing today.
Yeah, it was fun. Yeah, thanks. See you next time, I guess.
See you. Thank you. Have a nice week.
See ya. You too.